Okay, thank you. Thank you very much, everyone who joined. So today I'll talk about robust virtual diagnostics for accurate and confident beam properties prediction. So as you would see, there are like three distinct sections here. So it's the robust part, the virtual diagnostics, and the accurate and confident. So we will cover each one of these three parts. Sorry, could you please mute yourself? Okay, thank you. So this work was done with in collaboration with a wonderful team. So we have interns from UC Santa Barbara, people from SLAC, as well as Yarin Dal from Oxford. And so this is what we'll be talking about today. So we start with machine learning based virtual diagnostics, and motivation and background. Then we'll focus on spectral virtual diagnostics, and specifically we'll see 3 case studies. Each case study was done on a different machine, either with experimental or a simulation data. And each one of these case studies came to show another advantage of the spectral virtual diagnostics, either improved accuracy or prediction of fine features, or even going beyond the current diagnostic resolution. Then we'll switch gears into how we incorporate uncertainty. So this is the robust part, and then we'll summarize. So in any machine, and any accelerator machine, we want to have a good characterization of our beam in order to run the machine. But the problem, the current diagnostic methods to measure specifically the longitudinal phase space are destructive. So you can see here, we cannot use the beam and measure it at the same time. But this is exactly where we have the advantage for machine learning based diagnostics, because then we can predict the beam properties on a shot-to-shot basis and do it in a non-destructive way while we transport and deliver the beam to the experiments. So this is why we call it virtual or diagnostics, or machine learning virtual diagnostics. And the goal here is to get otherwise unavailable single-shot information about the beam in a non-destructive way, to improve the machine characterization, use it in optimization and data analysis. So how do we do it? So it's a supervised learning, meaning we have pairs of input and output. The output would be the longitudinal phase space image, and the input could be any non-destructive input that from the machine. For example, you can use the beam controls. In this case, or these readback scalars. If we use these readback scalars, we call it scalar virtual diagnostics. If we use the non-destructive spectral measurements, we call it spectral virtual diagnostics. But in any case, it's pairs of input and output, making it a supervised learning. Now, the nice thing with machine learning based virtual diagnostics is we only need to train the model once, and once it's trained, it's very fast to execute. And we can train it in either on measured data or on simulation data, or on both. So as I mentioned before, we could use for the input controls, for the input, we could use the control process variables. In this case, we call it scalar virtual diagnostic. It could be the input current, for example, or if we use the spectral data, we call it spectral virtual diagnostics. So there are several advantages to using the spectral information in the training, making the spectral virtual diagnostics a bit more robust. And here is why. So first of all, the readback scalars can sometimes be wrong, and then we'll have giggle, garbage in, garbage out, right? Then the readback scalars are integrated signals. So this means we cannot predict shot-to-shot fluctuation effects like microbunching. But the spectral is a much more direct measurement of what's happening in the accelerator. So we can use the spectra to find effects like microbunching, and we'll see it in the presentation. Now, the third thing is that bad predictions can result from discrepancies between what we think we're diagnosing, for example, here in the bunch compulsory 2 current and the XT cav current. In these cases, like we have in FACET 2, where we use very high current beam, having a discrepancy between the input and the output will result also in bad predictions. As you can see here from an earlier paper, all these dots right here are shots with bad prediction, meaning we had some input, but the output was, the predicted output was way off. So just to illustrate what is the pair of input-output for the spectral virtual diagnostics is that we have the full spectra. It's a vector like this, and each spectra corresponds to a different phase space image as shown here. Okay, so I hope I motivated you why we shall use the spectral virtual diagnostics. So now the question is, what is this exactly? So it's a neural network. Neural network is able to map millions of inputs to millions of outputs. And in our case, we learn the mapping between the non-destructive spectral measurement to the output, which is either longitudinal phase space, 2D images, or 1D current profile. We could train on both. We only need to train it once, as I mentioned, and then it enables us to do fast prediction of the beam. Here, I wanted to show that the virtual diagnostics class we wrote in Python is pretty easy to use, and it's basically composed of 3 main functions: get model, the machine learning model, construct the neural network architecture, feed the model using training data, and then predict the model using test data. And in this GitHub link, you can find example of the virtual diagnostic class. Okay, so let's take a look now at 3 case studies of the spectral virtual diagnostics. So we said we aim for accurate and confident prediction. So accuracy would come from designing the network architecture and the training process, and the confidence would come from various methods depending on the case. So here are the 3 cases: LCLS machine, LCLS-2, and FACET-2. For LCLS, we used experimental data, either 1D current profile or 2D longitudinal phase space images. And the confidence in this case came from comparing the output, the prediction from Scalar virtual diagnostics and spectral virtual diagnostics. And whenever there was a discrepancy between these 2, we flagged this shot. For LCLS-2, we used the superconducting soft X-ray simulation data. We simulate microbunching, so you can see here more fine features. And in order to get we can't use scalar virtual diagnostic in this case because the scalars are integrated signals. So what we did is we predicted the uncertainty from ensemble of neural networks. So I hope you can see here like these green patches. Those are the uncertainty interval. And for FACET-2, we use 2-bunch mode, Lucretia simulations. And here, to get a confidence, we're correlating the prediction with the spectral intensity. So let's take a look at each case study in more detail. So in LCLS, we show that spectral virtual diagnostics had an improved accuracy over scalar virtual diagnostics. And how did we do that? We collected experimental data, showing here. We just scanned several machine parameters. And then we trained on 4,000 examples, tested on 600 examples. For the scalar virtual diagnostics, we optimized the neural network architecture that it consistently had an improved prediction by 15% over previous networks suggested in this field. And the spectral virtual diagnostics, even with the optimized scalar network, it had lower mean squared error. as shown here in these 4 examples. So in green, we can see the neural network prediction from the spectral virtual diagnostics, in red from the scalar virtual diagnostics. So you can see that sometimes both were good, but oftentimes the spectral virtual diagnostics had an improved prediction. Here there are 4 spectra corresponding to each one of the examples shown. Now, another interesting observation that if we take a look here in this plot, we can see that these are all the test shots we had. And we see that the mean squared error in the color bar, it gets higher and higher as the current becomes higher. And why is that? It means that we had much worse predictions on high current shots, because we, as you can see here, we had less examples from these cases, like case number A. And therefore, the model was not trained well to predict this. So our MSE was high on this area, but is getting improved and improved as we go to the region where we had many examples. Now, here on the right, we can see the model calibration. What is the model calibration? Is the accuracy or percentage on shots with MSE smaller than some threshold, and then we scan the threshold. So you can see that consistently, the spectral virtual diagnostic gave us better accuracy over the scalar virtual diagnostics. Okay, so we could use the spectral virtual diagnostics also to predict images, as I mentioned. And even in the images cases, it did a better job than the scalar virtual diagnostics. So we can see here in the first column are 3 measurements. In the middle column is the prediction of the scalar network. And on the right is the prediction from the spectral network. And you can see that the spectral virtual diagnostics gave us an improved accuracy for these 2 shots. And the last shot is actually a very interesting one, because this was just white noise. There was nothing there. And the scalar network predicted it as a false positive, because it thought there was something there, but the spectral VD actually found it's a true negative. So I hope that at this point, we are convinced that the spectral virtual diagnostics give us some much better predictions. So now let's take a look at the second case. For LCLS-2, it has a 1 kilometer bypass line between the lineage and the undulator, and therefore microbunching instabilities are especially pronounced. And we want to be able to predict this because microbunching are the seed to the growth of some unwanted radiation modes in the free electron laser. So what you can see here is 2 simulations of the LCLS-2 superconducting soft X-ray. The input in terms of the scalar input to the simulation was exactly the same. But because of the instabilities, we got 2 different outputs. So this is the phase space output of the 2 simulations. And you can see that although the scalars were the same, the spectrum is different for the 2 simulations. This is because, again, the spectrum is a much more direct measurement of what's going on in the beamline. So then we trained an ensemble of neural network on 4,000 elegant simulations, and we predicted the current profile. And here you can see 2 examples. One example where the prediction was not so good, and we had high uncertainty, that's pink patches. And in this case, the prediction was excellent. So what we did is we took the mean squared error, or the normalized mean squared error, and we correlated it with the maximum predicted standard deviation. Now, you can ask, could ask me, Adi, why to do that? Because in real time, what we want to have is sitting in the control room and have a small monitor showing us the beam longitudinal phase space or current profile in real time. But we also want to get an idea of what's the error, how good the prediction is, right? But we don't have the ground truth in real time. So how can we get that? So we can see that by training an ensemble and having a predicted standard deviation, we can draw a threshold on the standard deviation and say, if the predicted standard deviation is smaller than this threshold, most likely it would be a good prediction. If the prediction has standard deviation higher than this threshold, most likely it's a bad prediction. So although in real time, when the model is deployed on the machine, we're not going to have the ground truth to calculate the mean squared error, we can utilize the predicted standard deviation to flag bad or good predictions. Okay, so FACET 2 is the third case. And with FACET 2, we wanted to push the spectral virtual diagnostics even a bit further. And we wanted to go beyond the current diagnostic resolution and see if we can gain an additional information by using the spectral intensity. And we could, since the spectral virtual diagnostic could able to resolve features that are beyond the measurement device limited resolution. So the TCAV, which is the measurement device, is capped at 35 kiloohms. It can measure more than 35 kiloohms. But sometimes, as you can see here on the bottom, we had high current shots like 80 kiloohms, but those on the TCAV will look like they're 35 kiloohm. So how can we distinguish between a real 35 kiloohms to a higher current shot, which just looks like a lower one on the TCAV? And the answer is, well, we can use the spectral intensity twice. Once to train the model, giving the spectrum and the current profile. But second, we can use the integrated spectral intensity, for example, from this band, and we can correlate the spectral intensity with the prediction. And as you can see here, there is a kind of linear relationship until it saturates. So this saturation occurs roughly at the TCAV resolution, meaning for higher current shots, we would have higher integrated spectral intensity here in this region, but they are capped at roughly 35 kiloohms, meaning those shots are really much higher current shots. So if we draw this threshold again, we could divide this space to high confidence region and low confidence region. And the spectral intensity allowed us to distinguish between good and bad predictions. Okay, so to summarize this part of accurate and confident predictions, we saw 3 case studies. The accuracy came either from customized neural network architecture or wider neural network trained longer in the case of microbunching, because we have many more features there to learn, or a customized neural network architecture, again, using the FACET 2 data. And the confidence came from either comparing the output of the 2 networks, Scalar and Spectral Virtual Diagnostics, and flagging bad shot, or either by correlating the prediction standard deviation from an ensemble of neural network with the mean squared error, or by correlating the prediction with the spectral intensity and to flag lower confidence region. So at this point, I want to switch gears and talk about how can we make this accurate and confident virtual diagnostics even more robust. And in order to be robust, we want to incorporate uncertainties. Now, why it's important to include uncertainties in particle accelerators? Now, when we deploy machine learning models in critical, safety critical systems like particle accelerators, we want to know what we don't know. And we want this information for analysis, control, and from safety perspectives. So the uncertainty quantification, or having this standard deviations around the prediction, help us to capture more outputs that are possible from the machine given one state. And it could provide us much more accurate beam information. So, for example, if we look at the weather forecast, they say, okay, it's going to rain today, but it's going to rain with 40% chance, right? So this is exactly what we want to have here. Like, this is the current profile beam, but the chances it's maybe has this different standard deviation intervals, and this is how we're confident in this prediction. Now, for control, is because we're using tuning and optimizations loop, and we could use the virtual diagnostic to, for example, in Bayesian optimization loops, to choose the next state of the system. And if we want to avoid uncertain state systems, we could save valuable tuning time. But not only save valuable tuning time, we could also avoid unsafe control actions that could lead to damage to our system. But the problem with neural network is that they're not aware of what they don't know. So, for example, new shots might be out of the trained distribution, so then the prediction would be unreliable, but we won't know that in real time. So the way we do it is we estimate the standard deviation along the prediction of the mean. Now, generally speaking, we have epistemic uncertainty and aleatoric uncertainty, where epistemic uncertainty is literally what the model doesn't know, but we can reduce it by adding more data. So it's called a reducible uncertainty. With aleatoric uncertainty is what we cannot understand from the data, and this is the experimental error or the inherent measurement noise. Now, there's several methods out there to include uncertainty. For example, Bayesian neural network or Gaussian processes, which inherently has uncertainty in them. But in our case, we use non-Bayesian approaches like ensembles and quantile regression, simply because they're easier to train on and they scale really well with the data. So our goal here was to quantify the reliability of the prediction. And the ensemble methods, it's a collection of neural network which allow us to cover for the epistemic uncertainty. And quantile regression is neural network with a tilted loss function to predict each of the quantiles. And in this case, we capture aleatoric uncertainty. Now, for the ensemble methods, we investigated few types of ensembles. So, for example, we could think of, if this is the neural network, we could think about random initializations of the weights and the biases as an ensemble with different randomizations. Or we could do random data split and having each bucket of data, having prediction from each bucket of data, and then aggregate the ensemble prediction. So here are the results. So with the ensemble, we examined random initializations. We looked at random subsets of the data without replacement, and we looked at bagging, which is random initialization plus random bags of data with replacement. And first thing we did is to to look at the ensemble mean squared error because we didn't want to have uncertainty but compromise our mean prediction, right? So here we can see the mean squared error versus ensemble size for the three different types of ensembles we used. And we eventually chose the bagging method to move forward with. And another metric I wanted to introduce today is the accuracy. And the accuracy, the way we calculated it, is how much of the measured value falls within the ±2 standard deviation bounds. So here is an example of an image prediction of a beam, and in red are the pixels that are accurate, meaning the real measured value falls within ± standard deviation. And here is the accuracy measurement. The standard deviation is the standard deviation of the prediction itself, as a standard deviation of the ensemble, and these are the two metrics that we use: accuracy and standard deviation. One of the problems that we saw is that we have translational error. So the prediction was very good, but it was just appeared on a different location in a space. Now, we don't care where it is exactly. We cared more about the shape of the prediction. So what we did to alleviate this translational error is we did a center of mass correction during the training. So we would take the center of mass of the prediction, and we would shift it to the center of mass of the true measured value. And you can see here that before and after the training with the center of mass correction, we were able to reduce our mean squared error by 65% and increase our accuracy by 60%. Okay, so how do we evaluate our model robustness? So one way to do it is to introduce an out-of-distribution example, meaning this is an example that was not used during the training. For example, it could be changing the machine setting. And the idea is that an out-of-distribution example would manifest higher uncertainty. So here we can see an example of the spectral information of the test shot in green within the trained distribution, and red is an out-of-distribution shot. And the corresponding predictions of the two, we can clearly see that the out-of-distribution example manifested in worse mean, but also much worse standard deviation, bigger standard deviation. So this is how we evaluate our robustness to an out-of-distribution examples. Another thing that we tried is to learn something about the machine, and not just to use the model to predict. And one way to do it is to train a bottleneck architecture, neural network architecture. For example, like this, you have input, you decrease your network size into some bottleneck layer, and then you increase it again to the output. And by training a neural network architecture like this, we force all of our examples to go through some shared, smaller shared layer. And then we took this bottleneck layer or latent space, and we wanted to see if we can learn something back about the machine. So what you can see here is the test shots, the latent space of our roughly 800 test shots. And we reduced the latent space size from 64 to 2D using we clustered it using t-SNE, and we reduced it using PCA. And we can see that shots are grouped by shape and maximum current in the latent space. So The latent space has some smooth transition from low current to higher current. And also each group like this in space corresponds to a different shape of the beam. So we hope that this would allow us to get insights to what is important in the spectra and what is important for us to learn. And intuitively, maximum current and shapes are the two main indicators or two main characterizations of the longitudinal phase space. So to summarize, we saw today spectral virtual diagnostics as a non-destructive shot-to-shot bunch diagnostics. We saw that the spectral virtual diagnostics increased the confidence and improved the accuracy. We looked at how to quantify the robustness of the prediction by using out-of-distribution examples, and we looked at bottleneck architecture to learn some interpretable latent space. So this is the bottom line, that I think that machine learning-based virtual diagnostics with quantified uncertainties for single-shot prediction will be able to provide us some additional information to do analysis, tuning, and control. And this summarizes my talk, and I'd be happy to answer any questions now.